So we created a transformation matrix. The question is why. So we have that some vector S is equal to our A matrix times the same vector, but just in a different reference frame. And let's go ahead and remind ourselves that these are vectors. And we'll draw our coordinate systems just to remind ourselves what they look like. S, when we have it in just S, we're referring to it in its global coordinates. What is it with reference to our standard X and Y? While S prime is referencing S in our local coordinates. So in this example, it's within a hill or within an angle. And A is a transformation matrix that will let us go from our local coordinates back to our global coordinates in case we want to see some reference. Now, I'm not going to get into the how just because it's a lot of advanced math. I can talk to you about it in office hours, or you can Google it. But our A matrix, cosine phi minus sine phi, cosine phi, is what's called an orthogonal matrix. So if you'll recall from last class, we had that A matrix times its inverse will equal the identity matrix. Well, in this case, the inverse of A is also its transpose. So if we take A and we multiply by A transpose, so that's where we switch what is a row and what is a column, we'll get the identity matrix. And that's an orthogonal matrix. We can derive it. Again, I'm not going to just because I'm not going to quiz you on it, and for now you can just take me at my word. But what that means is that we can take that A transpose matrix, multiply it on both sides, and we end up seeing that our A transpose times our global coordinates gives us our local coordinates. So our transformation matrix will let us go from local coordinates to global coordinates, and global coordinates, when we take the transpose, to local coordinates. And we have that the transpose, instead of having cosine phi and minus sine phi as our first row, it becomes our first column. So cosine phi minus sine phi, and then sine phi cosine phi, instead of being our second row, is now our second column. And we can use this. It's a lot easier to find a transpose than it is to find an inverse of a matrix. So this is very convenient for us as we go into analyzing linkages.